We've talked about Gauss's law for electric fields. Now let's talk about Gauss's law for magnetic fields. Let's say we have a magnet here and field lines running much like they normally do for a bar magnet. And now let's pick a Gaussian surface that doesn't include the magnet. So let's say, I don't know, a surface like that. Now what is the total surface integral of all the magnetic flux across this surface? Well, every field line that enters also leaves. So what this means is that the total surface flux has to be zero. So the surface integral over any closed surface that doesn't include the magnet of the magnetic field vector dot the normal vector dA equals 0, which is Gauss's law for magnetism. It's saying that any volume that doesn't include the magnet itself, the total number of field lines in equals the total field strength out, so the total surface integral is 0. You could have situations, for example, a surface like here, where you get a lot of very strong field lines coming in around here and a lot of relatively weak fields coming out there, but they still balance out. Small area, strong field here, big area, weak field over there. So far, very much like Gauss's law for electricity, or Gauss's law for radiation or anything else. The difference is what happens if you actually define a Gaussian surface that includes the magnet. Well, in this case, you get field lines that leave, but they all circle round and come back in again as they go to the other pole of the magnet. And you get field lines that are purely inside, which don't count because they don't cross the surface. So the amazing thing is, for magnetism, this is true even if there is a magnet inside your volume. So it's different from the electricity one, where if there's a charge inside, it's not equal to 0. Here it's always equal to 0. That's because whenever you get a north pole, you also have a south pole, and the field goes from one to the other, so any field line that enters must come back at the other side. Now the one exception would be, what if you actually had a monopole, a pure magnetic north pole with field lines just coming out from it. Now there's nothing in the law of physics, as far as we know, that says these are impossible, and if they did, the surface integral would equal the number of monopoles inside, probably with some constant, mu naught or something in it. But as far as we can tell experimentally, monopoles do not exist. But that's an experimental thing. If one day you do one of these surface integrals and find it doesn't equal to 0, that will tell you you've caught a monopole. And indeed there are experiments in basements around the world trying to find monopoles that might be flying through the Earth from deep space. But at the moment, as far as we know, there are no monopoles. Whenever you have a north pole, you also have a south pole. Therefore the fields loop from one to the other. And as they're looping any surface at all, one that includes the magnet, one that doesn't include the magnet, any funny shape that does both, doesn't matter. Surface integral is 0.